What lies inside these towering masses of enigma, also known as black holes? Join us to the far reaches of this black hole to learn more about what's inside. If you're interested in keeping up to date with news about the universe and its surroundings, subscribe to our channel. Be sure to like this video so it reaches more people, and turn on the notification bell. It all started in 1916 with Albert Einstein's general theory of relativity. Einstein was the first to predict the existence of these entities, although the term black hole was officially coined 50 years later. In the decades that followed, some scientists already believed in Einstein's theory, while others dismissed it as speculative or even absurd. It was in the late 1960s, when researchers were studying the constellation Cygnus X1, that they noticed something amazing. A strange, bright blue star was emitting X-rays, revealing that it was no ordinary star. This blue star was orbiting around something giant and dark. Upon further investigation, scientists discovered that the X-rays were not moving on their own but were being attracted to the mysterious entity that the star was orbiting. Whatever was at the center of that orbit turned out to be a powerful force that consumed everything around it. At that point, science gained official evidence that black holes were a reality, but little did scientists know that things were about to get even more extraordinary. That initial discovery of Cygnus X1 turned into a series of additional revelations. Soon it was proposed that there could be approximately 100 million black holes in our Milky Way galaxy alone. However, due to their incredible difficulty to detect, since they emit no light and only indirectly reveal their presence via gravitational influence, we still do not have an accurate and precise count. According to current estimates, the number remains in the several millions, which makes black holes even more important objects of study. According to most physicists around the world, a black hole is an entity where anything that enters is compressed astronomically until it becomes a singularity. To simplify it into clearer words, researchers have explained that due to how black holes work, if someone were to fall into one, they would stretch like spaghetti, slowly being torn apart in this noodle form before reaching the final spaghetti state. This is one of the scariest parts of research done on black holes, and also what makes everyone want to know all the details. Although the closest confirmed black hole to Earth is roughly 1,500 light-years away, this information still raises the question: could a black hole actually swallow the Earth? In April 2021, scientists managed to publish the first clear photograph of a black hole, specifically the supermassive black hole in M87, the galaxy Messier 87. The black hole was photographed over several nights in a row, and with each image, researchers collected more and more evidence about its structure. These observations revealed the existence of three fundamental layers in its structure. That's right, a black hole is not just a lone hole in the void. To delve into the depths of its mystery, we must understand the first two layers. First, there is the outer event horizon, a boundary that surrounds the mouth of every black hole. Once something reaches this point, it cannot escape. It is either trapped there or pulled deeper on its journey toward the singularity. The singularity, on the other hand, is the central core of the black hole where gravity is so intense and constant that literally nothing can get out. To escape, something would have to travel at a speed much faster than light, which has so far proven impossible. It is important to note that gravity on Earth works in a far more benign way. If gravity on Earth operated like it does near a black hole, we would not be able to survive as we do. Once we cross the event horizon, there is no turning back. We face black holes, the great ultimate enigma. The singularity is the point at which most of the mass of the black hole is concentrated, where everything is compressed into what might be called practically nothing. Physics as we know it stops working in that region. It becomes absolute chaos. The worst part is that each black hole is unique, with a different gravitational force and pattern of attraction. That means that learning everything about one black hole only to move to another forces us to start from scratch. It's like a never-ending, shifting puzzle. The problem is that scientists cannot study black holes in the same way they study stars or planets. They can't just look at the radiation they emit, or the dust and gas that swirl around them. And they cannot send probes, like Voyager, into the interior of a black hole, because as we established, the probe would be crushed upon reaching the singularity. Simply put, our only option is to study these massively powerful phenomena remotely, in 2 dimensions, from the outside. The fact is that we have not been able to get inside the singularity to really find out what it is, because as we have established, traveling faster than the speed of light is effectively impossible. However, that does not mean that scientists who have been studying these giant masses of mystery do not have their own theories. They propose numerous theories about what could lie inside a black hole other than the singularity. One of the most plausible, intriguing theories suggests that black holes are not just voids of nothingness, but that beyond the event horizon, and at the beginning of the zone we commonly call the singularity, there could be something else entirely. This theory suggests that black holes could be like doors, but not doors leading to conventional spaces. Rather, they may be portals connecting different galaxies, or even universes. Another fascinating theory posits that black holes could be a glitch in the cosmic matrix. Using a futuristic, metaphorical reference, if we could one day develop technology capable of faster-than-light travel, we might be able to open our own pathway through a black hole and explore what lies on the other side. These theories remain speculative, but scientific exploration continues in search of more concrete answers. Some researchers suggest that the singularity is not simply a void but may actually be a wormhole, an Einstein-Rosen bridge, leading to another galaxy. That would be a shortcut in interstellar travel, something we never thought was possible. This idea raises the possibility that we might not be restricted to exploring only planets in our own solar system. We might eventually look for ways to traverse black holes to reach the universes they connect to. If true, that could break open the very concept of distance and frontier. At the other end of the speculative spectrum lies a theory that denies the existence of black holes altogether. Tokyo-based scientist Enrico Raldi and his team have proposed a radical reinterpretation. Perhaps these phenomena, and the effects we observe, are holograms. Now, holograms as we know them are created through technological means. But in this theory, any visual discrepancy or perceptual illusion can be considered a hologram as well. When we speak of a black hole's gravitational lensing or event horizon, maybe we are watching a projection, a boundary that behaves like a hologram. Raldi's theory suggests that our observations of black holes may reflect the limits of our instruments and concepts rather than actual singularities. Perhaps gravity, light, and matter are more deeply unified than the equations suggest, and that what we call a black hole is just the surface manifestation of a more complex, holographic reality. Critics argue that this holographic hypothesis may sound like science fiction, but it does have a basis in certain interpretations of quantum gravity and information theory, especially the holographic principle, which posits that all information contained within a volume of space can be represented on its boundary. That is, the universe itself may function like a hologram in certain respects. Another compelling notion is that, rather than vanishing into oblivion, information swallowed by black holes might be encoded on the event horizon and radiated back out, a concept based on Stephen Hawking's ideas about black hole radiation and information paradox resolution. According to this hypothesis, black holes might preserve, transform, or even transmit information across dimensions. Some propose that advanced civilizations, aware of these properties, could use black holes as cosmic hard drives, or even gateways. Other physicists invoke string theory to suggest that singularities aren't infinitely dense points at all, but perhaps membranes or bands in higher dimensional spaces. In certain interpretations, a black hole in four-dimensional spacetime corresponds to an entirely different, and potentially navigable, reality in 5 or more dimensions. That perspective transforms each black hole from a gravity trap into a multidimensional nexus. Of course, any of these ideas, however mind-bending, remain hypothetical. Observational astrophysics has limitations. We cannot place instruments inside a singularity. But we can continue to watch how black holes influence their surroundings. For example, future telescopes such as the Event Horizon Telescope and next-generation X-ray and gravitational wave instruments may reveal new signatures, echoes of quantum effects or signs of information retrieval at the edge. Meanwhile, supercomputer simulations are becoming increasingly sophisticated. Scientists are modeling black holes not just as points but as dynamic systems with magnetic fields, jets, time dilation effects, and quantum thermo interactions. Combined with data from gravitational wave detectors such as LIGO and Virgo, these simulations aim to probe deeper into claims about the interior structure, whether wormholes, holograms, quantum foam, or other exotic constructs exist. To understand these structures better, astrophysicists analyze the radiation escaping from accretion disks, the jets launched by magnetized plasma near poles, and even echo mapping of rebound signals around event horizons. Each observation refines our models and challenges our preconceptions. At the same time, interdisciplinary collaborations are emerging. Mathematicians explore the zeros and singularities of Einstein's equations. Quantum information scientists examine what happens to entangled pairs when one particle crosses the event horizon. Philosophers interrogate the meaning of singularity and nothingness. Still others propose that black holes may one day be harnessed, generating Hawking radiation for power, or creating controlled wormhole access, though those remain speculative. So where does that leave us now? We stand at an intellectual crossroads. Black holes may be far more than cosmic vacuum cleaners. They might be cosmic Reuters, gateways to other regions or realities. They might be vaults of encoded information. They might even be illusions, holograms cast by the deep structure of space-time itself. One thing is clear: every black hole we observe acts as a teacher, challenging relativity, thermodynamics, quantum mechanics, and the nature of reality itself. As astrophysical observations improve, we may one day gain a conclusive answer about what lies inside those towering masses of enigma. For now, the journey continues, guided by Einstein's pioneering insights, informed by the first images of M87, propelled by theoretical leaps from holographic polymers to wormhole brands. Every step into black hole research brings us closer to understanding not only the fate of collapsed stars, but possibly the boundaries of the universe and of human knowledge. The universe is full of mysteries, and black holes may be among the greatest. We cannot look inside them with probes, but we can study what gravitational waves, X-rays, and orbiting stars tell us. We can continue to refine our math and theories, build better instruments, and dare to explore ideas that bridge physics and philosophy. From their first prediction in 1916 to their public naming 50 years later, black holes have revealed themselves to be far more complex than mere cosmic monsters. Rather than consuming and annihilating, they may connect realities, preserve information, or even distort space-time into shapes beyond human intuition. As we move forward, we may one day solve the enigma, but until then, each new discovery reminds us of one profound truth: that sometimes exploring the darkest, most unknowable places in the universe lights the brightest flame of human curiosity and wonder. In the wake of our deepest forays into black hole research, humanity finds itself standing at the threshold of a vast intellectual frontier. What began as a mathematical oddity in Einstein's 1916 field equations has, over the last century, transformed into one of the most profound and mysterious subjects in modern science. But in that transformation lies a paradox. The closer we get to understanding black holes, the more they seem to slip through our intellectual fingers, revealing new layers of complexity and contradiction. Take, for instance, the information paradox, one of the most enduring puzzles in theoretical physics. According to quantum mechanics, information about the state of a system cannot be destroyed. Yet, black holes appear to devour matter and then evaporate via Hawking radiation. If all that matter disappears, does the information vanish too? Stephen Hawking, back in the 1970s, proposed that information might be lost forever, an idea that undermined a central tenet of quantum theory and ignited decades of fierce debate. Some argue that this paradox could be resolved if black holes are not true singularities but instead gateways, wormholes or Einstein-Rosen bridges, that connect to parallel universes or other regions of space-time. Recent theoretical models even posit that black holes are fuzzballs, quantum structures without a definable event horizon but instead a tangled web of strings or microstates. According to string theory, each microstate encodes part of the information about infalling matter. What we perceive as an event horizon might be a statistical blur of these states. If true, black holes might not be final, dreadful endpoints, but rather information-preserving cosmic objects, strange and fascinating in their behavior, but not destructive. Meanwhile, observations continue to challenge theorists. The 2019 image of M87's black hole was soon followed by snapshots of Sagittarius A*, the supermassive black hole at the center of our Milky Way. When astronomers observed Sagittarius A*, they found that its surroundings were far from calm. Instead of a smooth, glowing ring, its accretion disk displayed turbulent streams, rapid flares, and magnetic loops. This turbulence suggests that black hole environments are dynamic places, constantly changing, unforgiving, and unpredictable. More recently, gravitational wave detectors such as LIGO and Virgo have picked up collisions between black holes, dramas unfolding far beyond the Milky Way. These events send ripples through spacetime itself. When two black holes merge, they generate energy in the form of gravitational waves equivalent to the mass energy of several suns. When scientists first heard these cosmic collisions in 2015, they realized that black holes are not just passive objects, they can be violent and interactive. Each merger opens a window into regimes of gravity so extreme that they test Einstein's theory in previously unreachable regimes. Even the simple question of a black hole's interior geometry is snowballing into a surprising field of inquiry. Classic general relativity implies that crossing the event horizon leads to inevitable collapse into singularity, a point of infinite density and zero volume, where spacetime curvature becomes infinite. But recent quantum gravity models propose otherwise. Some maintain that the core of a black hole could be a dense Planck star that eventually rebounds, spewing information back into the universe through a slow leak of radiation. Others imagine the center as a high-energy region where space and time invert, giving rise to exotic topologies, a sort of cosmic Mobius strip of spacetime. Crucially, this means that the idea of a black hole interior is no longer necessarily restricted to doom and destruction. It may instead offer a gateway to new physics. If we could ever peer inside, we might find